Good morning. I'm Alice Roffi, a research fellow at the University of Florence in the field of STEM education supported by digital technologies. I have a master's degree and a PhD in biological field and another PhD in educational science and psychology. In this video, we will explore what inquiry-based learning is, focusing on the features of this teaching strategy, exploring the educational benefit in the context of STEM teaching for higher education. The IBL is an educational strategy where students actively engage in the construction of knowledge through a process similar to that of professional scientists. It's about discovering new relationships, formulating hypotheses, and testing them through experiments and observations. IBL emphasizes active participation and the learner's responsibility for discovering knowledge that is new to them. This approach can be used to solve problems and involves the application of several problem-solving skills. The inquiry process is often organized into distinct phases that form what we can call an inquiry cycle. While different variations exist, our discussion will be based on a framework developed by pedestrian collaborators, including five distinct inquiry phases: orientation, conceptualization, investigation, conclusion, and discussion. Let's look at each phase more in detail. The initial phase is the orientation, that focuses on introducing the main theme or problem necessary for conducting the subsequent activities. At the end of this step, students formulate the problem statement. The following phase, the conceptualization, aiming at understanding the concept, resulting in the final definition of the research question, which led to the development of the hypothesis. The next phase is the investigation, which represents the inquiry step in which students are engaged in planning how to test the hypothesis generated in the previous phase and how to collect, analyze, and report the data. This step could generate further question of hypotheses. Thus, the process orientation, conceptualization, investigation can start again. The data interpretation is the final result of this step. In the conclusion phase, students are involved in the hypothesis verification, evaluating if they are supported or not, considering the interpretation of data. The outcome of this step is the final conclusion about the findings. Finally, the discussion phase represents the metacognitive dimension of the IBL, in which students reflect on the whole IBL process or on a single phase of this strategy. They might consider the success of their process, propose new problems, and suggest improvements for future inquiries. Now we look at the IBL benefits for STEM teaching. In the context of higher education, this approach promotes self-efficacy, task commitment, intrinsic motivation, and creativity, even though its use is not so widespread. The research studies on the use of this method in higher education highlight the application of IBL in university courses, especially those on STEM, entails several benefits, such as improved student retention and motivation. Moreover, students acquire research competencies that provide valuable in their professional careers. This strategy not only benefits students' learning, but also contributes to educational innovation. In fact, it empowers teachers to adopt an innovative teaching approach, which can be successfully transferred to and adapted to other courses, thereby promoting a broader transformation in teaching practice. The possibility to conduct the IBL collaboratively led to positive impact on students. By working together, students engage in a collective search for solutions, fostering deeper understanding. Collaborative inquiry can also lead to socio-cognitive conflicts, which stimulate critical thinking and cognitive development. Furthermore, the development of collaborative transversal skills is increasingly important in university teaching. The integration of digital technologies further amplifies the benefits of IBL. Computers-based learning environments assist students in managing routine tasks such as data organization, calculation, and information retrieval, allowing them to focus on high-order inquiry processes. These tools also foster self-regulated learning by enabling students to independently access information and instructional support, increasing motivation and engagement. Empirical research confirms that the web-based guided inquiry, that is, digital learning environments designed for supporting the IBL process, enhance various inquiry skills, including problem identification, hypothesis formulation, experimental design, and data analysis. By breaking down complex scientific processes into manageable steps, technology-supported inquiry learning promotes authentic scientific discovery and critical thinking. An example of integration of digital technology into inquiry practice was offered by a researcher, Julie Corriel, and colleagues that developed the Personal Digital Inquiry Framework, providing theoretical, practical guidance and support models for teachers in designing educational activities. This implies, for example, to use digital tools for searching online information during the initial phase of IBL, or take digital notes or make some diagrams during the investigation phase. In conclusion, IBL offers a powerful approach in higher education, fostering essential skills and deeper engagement with learning that extend beyond the conclusion. Thus, it is a valuable strategy for engaging students in authentic scientific practices and promoting STEM learning and further skills. In the next video, the aspect discussed here will be faced from a practical perspective, looking at how to implement them in the teaching practice.